Alright, welcome to the lecture on G2 instantons. The plan is we will start with a little general introduction to motivate why we're doing all the things we're doing anyway. Then I will explain the words from the title, starting with G2. So I will talk about the linear algebra of G2. Then the other word from the title, instantons, I will explain what are ASD instantons and G2 instantons. And then the main part of the talk will be a construction of G2 instantons. That will be the construction from Walpusky and a generalization that I proved. Right, so let's jump right in with the introduction. To this end, say we're on some Riemannian manifold, MG, and we have some curve in that manifold. And let's say it's a closed curve, so gamma of 0 equals gamma of 1 equals some point x. Then because we have the Riemannian metric, we have a Levi-Civita connection, and because of that, a parallel transport along the curve. Say P gamma, and that will be a map from the tangent space in the starting point to the tangent space in the end point, which in our case are the same point. So the picture is like this. We have our manifold here and some starting point x, and then a curve gamma in this manifold. And let's say we start with some vector in the tangent space of x. We transport it all the way along gamma. And end up with some other vector in the tangent space of x. And as you can see in this example here, we started with one vector, and after transporting, we ended up with a different vector. So, so this map P gamma, this linear transformation, can actually be checked to always live in the orthogonal group of the tangent space. So it preserves the metric at that one point. And we can, if we want, identify OTXM with ON. And given this, we can define the holonomy group of a metric, namely hol G is the set of all P gamma, where gamma is just some closed curve, and because of this identification one line above, we can view this as a subgroup of ON. The picture tells you ON need not be trivial. It can be something that's not just the identity, but the question is, what can it be? What are the possible holonomy groups? And the answer is maybe not as many groups as you thought it could be. So the theorem by Berger from 55 says there are essentially 7 possibilities for hol G. It could, for example, be, like in the case that I've drawn. In the case I've drawn, I drew a 2-sphere, and the holonomy group will turn out to be SO2. So it could be that the holonomy is SON, and that would be on a manifold with dimension n. It could also be UN. That would then be called a Kähler manifold, and that happens on manifolds with dimension 2m. Well, let's give that a different name. Let's say UM, and that's on m-dimensional manifolds. And then there are a bunch of other options. Let's not go through all of them. But what we do need to know, there's one exceptional option, and that's the holonomy group G2. And that can only occur in dimension 7, mysteriously. So if you later bother to look up that theorem, you will see that the word essentially that I wrote here does a lot of heavy lifting. There are other holonomy groups that you get from symmetric spaces and finite quotients, for example. So you have to be careful with what I mean by the word essentially. But let's not worry about this. All I wanted to say is this holonomy group G2 is very interesting. Now, this theorem only tells you that it's a possibility this holonomy group could occur. But it wasn't clear for a long time whether there actually are spaces with this holonomy group. They were eventually constructed, and the first compact example was constructed almost 40 years later. So that's a theorem by Joyce from 94, which says there exists a compact Riemannian manifold, say Mg, with holonomy equal to G2. So that took a lot of work to get there and a long time. But since then, we came up with some millions examples. And some thousands of them can be distinguished by their homology. So when you see these numbers, millions, examples, thousands can be distinguished by homology, you immediately ask yourself, well, how many of them are essentially the same thing? Did we maybe just write down the same manifold 1,000 times each time, and through this end up with 1 million manifolds? Or maybe are they different in some other way that cannot be detected by homology? So, how many examples are essentially different? And that's a hard question, and one possible attempt to answer that question is using gauge theory. And the hope is that maybe one can use invariants defined using gauge theory to answer this question here. Now, the motivation of this came from dimension 4. There we have Donaldson theory. And that was used to distinguish some manifolds that can't be distinguished by homology alone. For example, we have the exotic R4s, which are homeomorphic to R4, but not diffeomorphic to R4. So they have the same homology, but they will have different Donaldson invariants. Right, so that's the overall goal. In the end, we want to use some gauge theoretic objects to define invariance. That said, let's jump into the actual mathematical content of the lecture, and I will start explaining the words from the title. So let's start with the linear algebra of G2. And I already said G2 is a 7-dimensional thing, but for reasons that will become clear later, I will have to start to explain some 4-dimensional geometry. Right, so on C2, we can choose real coordinates, say y0, y1, y2, and y3. And then we can write down a hyperkähler triple on C2 as follows. We can say omega 1 is dy0 wedge dy1 plus dy2 wedge dy3. And then we can cyclically permute these 3 indices to get 2 other 2 forms. We get omega 2, which is dy0 wedge dy2 plus dy3 wedge dy1, and omega 3, which is dy0 wedge dy3 plus dy1 wedge dy2. And one immediately observes that they are invariant under the map -1 on C2. So I just literally mean the map which sends x to minus x. And because of that, if you want, you can view omega 1, omega 2, omega 3 as 2 forms on the orbifold C2 mod plus minus 1. Now, orbifold is a big word, and it's not strictly necessary to do all the stuff that we are doing. So if you don't like it, just think of omega 1, omega 2, and omega 3 as 2 forms on C2 mod plus minus 1 minus the 0 point. That's then a perfectly smooth manifold. Now, from algebraic geometry, we get the blow-up of the complex variety C2 mod plus minus 1 in 0. And that would be, well, a smooth manifold of real dimension 4 living over C2 mod plus minus 1. And from algebraic geometry alone, we get that this is a complex surface. So we endowed C2 mod plus minus 1 with some complex structure that defines us the blow-up, and we get a complex structure on X. But we have even more than that. We have that the whole hyperkähler triple survives on X. So that was first realized by Iguchi and Hansen And they say there exists omega 1 twiddle, omega 2 twiddle, omega 3 twiddle, two forms on this space X, which is a hyperkähler triple. And not only that, this hyperkähler triple is asymptotic to the flat hyperkähler triple in some sense. And that sense is that, well, if you push forward omega I twiddle and you compare it with omega I, this is of order r to the minus 4, where r is the distance to 0 in C2 mod plus minus 1. And this is true as r goes to infinity. So the picture for that is the following. We have our singular space here, C2 mod plus minus 1, has this singular point here, and then comes the blow-up, which gives us a map from the blow-up to the singular space. And let's write that as XEH for Iguchi-Hansen. And there, this one singular point has become a two-sphere. But more importantly, the whole space XEH is now a smooth manifold. So much to 4 dimensions. Now we get to the actually relevant part, which is 7 dimensions. And, well, you could give a definition of G2 using the cross product of R7. That may be the most intuitive. But for practical analytical reasons, it's better to define it differently. So I'll give this different definition now. It may not make a whole lot of sense when seeing it for the first time, but it turns out it's the most practical to work with. So that's why people keep using it over and over. And the definition goes like this. I now write down a 3 form, phi 0 on R3 times C2 as follows. We say it's dx1, which dx2, which dx3, minus, and then sum from I equals to 3 over dxi, which omega I, where dx1, 2, 3, those are coordinate 1 forms on R3, and omega 1 to 3, that's this hyperkähler triple on C2 from before. And given this 3 form, you can set G2 to be the stabilizer of phi 0 in GL7R. So whatever it is, this stabilizer is going to be some Lie group, and we just call it G2. And of course, this is extremely well understood. All of the linear algebra of G2 is known, so a lot more could be said about this group G2, but because of time constraints, we're not going to say this here. Now that's the linear algebra picture. So that's on R7. And just like for metrics, you can now define what's a G2 structure on a manifold. So if we have a 7 manifold M and some 3 form, we say that this guy is a G2 structure if for all x there exists a linear map L such that L star phi 0 equals phi in that point. So here's our smooth 7 manifold. And we have some point x here. We have the tangent space in x and our map L going on to R7. And we have our standard G2 form, phi 0 on R7. And we exactly ask that phi 0 pulled back gives us phi x here on this tangent space. So yeah, it's completely analogous to the case of Riemannian metrics, which are just a metric in each point. Right, so that definition is extremely abstract. It doesn't tell you a whole lot, but the good thing is we can extract one extremely concrete object from such a G2 structure. And that goes like this. You can check that G2 is contained in S07. So what that means is, if you have a G2 structure that defines you a reduction of your frame bundle to G2, and therefore induces an S07 reduction. So in particular, what it gives you is is a metric G phi, but also an orientation, and therefore a Hodge star. And one very important theorem about G2 geometry is the following theorem, which says that the holonomy of this metric here, the holonomy of G phi, is contained in G2 if and only if nabla phi equals 0, where this nabla here is the Levi-Civita connection of G phi, so the metric induced by phi. So the reason that's important and the reason that's useful is if you want to write down a G2 metric, so a metric with holonomy contained in G2, you don't need to bother writing down a Riemannian metric directly, but you can actually write down this 3 form phi, which must be parallel. So it's still a hard task, but it turns out that makes the problem a bit more manageable than having to write down a metric on a 7-dimensional manifold. Right, let me give you one example of a torsion-free G2 structure. So a G2 structure satisfying this nabla phi equals 0. And to this end, let dx1, dx2, dx3 be parallel forms on T3. And let omega 1 twiddle, omega 2 twiddle, omega 3 twiddle be the hyperkähler triple on our Iguchi-Hansen space from before. In particular, you will find that they are also parallel. And what you can do then, if you have these gadgets, these dxi and these omega I twiddle, you can write down exactly the same formula as here, only instead of omega I, you write omega I twiddle. And that will define you a 3 form on T3 times x, and will turn out that this guy is torsion free. So I'll write it down again. Let's say we have the 3 form phi product, which is dx1, wedge dx2, wedge dx3, minus dxi, wedge omega I twiddle. So that's then perfectly nice 3 form on T3 times x EH. And exactly because the dxi were parallel and the hyperkähler triple is parallel, you will find that this thing is also parallel, as the phi product is 0.